Okay, so hi guys, and today we will be talking about iron carbide phase diagram. So what is this all about, and everything that can be asked during the material science for engineers class about this diagram. So what iron carbide diagram even tells us? So iron carbide diagram tells us that at certain carbon percentage, as we have here, this is carbon composition, and temperature, what phases and microstructures will still have, and whether it will be soft, hard, ductile, or brittle. Okay, carbon is strengthener, so if we add carbon, it can make it stronger, because the carbon sits between, like, let's say these are iron molecules, and we have here carbon. So carbon sits between iron molecules and blocks dislocation movement, therefore making it stronger. So more carbon usually means the material is stronger, harder, less ductile, and more brittle. Yes, adding too much carbon can make the material too brittle. Okay, now let's discuss phases and microstructures. So let's talk about phases and microstructures. So what generally the word phase means? So phase is chemically or structurally uniform material. So phase can be ferrite. For example, here we have ferrite, this is a phase, or austenite, or cementite. So ferrite, austenite, and cementite, these are phases. And then we have microstructures. So people tend to confuse microstructure and phase, so it is important to know difference. Phase is chemically or structurally uniform material, but microstructure is visible arrangement, or we can say mixture of phases. So this is microstructure. And what are examples of microstructure? We can have perlite, or ferrite plus perlite, or perlite plus cementite. So these are types of microstructures that you are going to encounter in iron carbide diagram. A lot of people think that perlite is also phase, but it's not a phase, it is just microstructure. So let's talk about main phases. So here we have ferrite, okay, and ferrite is BCC iron with very little carbon dissolved inside. So you can literally see that, like this tiny part here, this is the ferrite, and you can see that carbon composition is very low, and as we have discussed before, the higher the carbon, the harder the material, the stronger, the more brittle it is. So therefore, as we don't have much carbon in the ferrite, so the properties will be soft, ductile, weak, and it can also be magnetic. It can be magnetic below, let's say, about 768, somewhere here. Below that temperature, it can be magnetic, and it is stable at a room temperature. Okay, So, but why is it soft? As I mentioned, due to having little carbon, the dislocations can also move more easily. Next, we are going to talk about austenite, which we have here. So, austenite is FCC. Is FCC iron with more carbon dissolved inside relative to ferrite. So austenite, as you can see the temperature range, it exists at high temperature. It is non-magnetic. It is more ductile and dissolves much more carbon than ferrite. And one important point is that I'm gonna write it outside of table about austenite. Many important heat treatments start from austenite. So and why generally austenite can hold more carbon? Because FCC itself has larger interstitial spaces than BCC. So as you know, as I mentioned here, the carbon goes in these tiny spaces and they are called interstitial spaces. And this thing itself, when we have iron here and when we have small carbons, it is itself called an interstitial alloy, mix of two elements, right? And due to having more interstitial spaces, it is FCC. And lastly, our phase, we have cementite. We have here cementite. Cementite is basically an iron carbide, and this is the formula. And its carbon content, as you see the arrow here, is 6.7. The properties is that it's very hard, very brittle, strengthens steel but reduces ductility. It's hard because carbon strongly distorts the structure and blocks dislocation movement. Okay. And then we also have such thing as delta iron. You see here? Okay. Sorry, delta ferrite. This is delta ferrite. So delta ferrite is also BCC iron, but it only exists at very high temperature. So the thing is, like the ferrite is also BCC, and the delta, we have a delta structure, it is also BCC. Ferrite is the thing that exists at low temperatures, and the delta exists at high temperatures, but as you can see, their structure is same. So as we heat the material, so we will go from alpha here, BCC, we will go to austenite, which is FCC, and then we are going to return back to our structure BCC. So as you heat, even though in the middle of heating we can have FCC, we will still go back to BCC. Okay, and then here we have the Utictoid reaction. It is basically, we can say, the most important reaction in steel. So Utictoid reaction, as you can see, it happens at 0.76 carbon composition, and temperature is given here at 727 degrees Celsius. So what happens? So you see, when we have here exactly the middle of the reaction, we would call it eutectoid still. Eutectoid still. So what do we have? Eutectoid still gives 100% perlite composition. So if we were to draw the composition, it would be 100% perlite, and we are going to see it here. As you can see here, we have at this point we have the perlite forming. So this is the perlite structure. Just as the heat is decreasing, for example from here to here, as heat is decreasing, the perlite also starts to become how can I say, from more liquid phase it becomes the solid phase. So as it solidifies, the structure can also start forming different structure, but generally at this point the perlite forms. But we have hypoeutectoid structure and hypereutectoid structure. Hypoeutectoid is what is before. Here we have 0.76 carbon composition, right? So before that, what we have, we would say it hypo, and what we have after, we would call it hyper. Okay, so we have hypo and we have hyper, and as we have hypo, our structure, like our products, are ferrite and perlite. You see, ferrite and perlite. But here we have perlite and cementite. So we can also write that if we have hypoeutectoid steel, our products, like our final slow-cooled microstructure, would be ferrite plus perlite. But if we have hypereutectoid steel, it would be cementite plus perlite. Okay, so the only thing that is staying the same, we have perlite, and here we have, before we have extra ferrite, and after we have extra cementite. Okay, and the eutectoid reaction, as you can also observe here, the eutectoid reaction can be written as alpha plus, we see here, cementite. So ferrite plus cementite would be the final, the formula, we would say. So itself we can also write as this plus cementite. So it means austenite gives us ferrite plus cementite. But visually, ferrite and cementite form as alternating layers, okay? And that layer, the structure is called perlite. So we can also understand that perlite means ferrite and cementite forming as alternating layers. So we would call it perlite. Okay, and then we have the difference between, so we have here our eutectoid reaction and we have here eutectic. Okay, and what is the difference? In eutectoid, the solid is transforming, so basically the reaction happens in the solid phase, but here, as you can see, the liquid transforms. Okay, so liquid gives the result of two solids. In the eutectic reaction, we can write it as liquid gives the reaction of two solids, but in eutectoid, the solid gives reaction of two solids again. Okay, then about perlite properties here, Pearlite properties are that it is harder than ferrite, but more ductile than cementite, and it has a balanced strength and ductility, the pearlite. So this is basically the pearlite structure. As you can see, we have alternating layers. So these light layers, these are, you can see, they are the ferrite layers, and the dark layers that we have here, these are cementite layers. So if you were asked to draw the microstructure of pearlite, you would draw again something as here. You would have to combine the cementite and ferrite structures. Okay, then what we have? We have let's talk more about hypereutectoid steel. So in hypereutectoid steel, here, hypereutectoid steel, carbon composition is more than 0.76 percent, right? So we can say, like, example is 1% of carbon steel. So it has extra carbon, therefore it has extra cementite, right? And in high temperature, it is all austenite, like, let's say, and if it goes below this temperature, the cementite starts forming first. Okay, so as it cools, this cementite starts forming first, and this early cementite is called proeutectoid cementite. And at exactly this temperature, remaining austenite transforms into pearlite. Okay, so, and the proeutectoid, the word proeutectoid itself, you can hear the things such as like, it's the phase that forms before the eutectoid reaction. So before basically the reaction itself happens, we can have the proeutectoid phase. So what is proeutectoid phase? In hypoeutectoid steel, proeutectoid phase is ferrite. So the thing here, the differentiating things, you would call it as proeutectoid phase. It's here it's ferrite and here it's cementite. In hypereutectoid, the proeutectoid phase is cementite. Okay, and one more interesting question to explore: why pearlite? So we see here the, hold on, yeah, we see here the pearlite. So why even pearlite forms layers? Why pearlite forms layers? So austenite has medium carbon, and when it transforms, ferrites wants almost no carbon, but cementite needs a lot of carbon. So here we have kind of opposition. The ferrite does not want carbon, but cementite needs carbon. So our carbon atoms must diffuse, and the structure organizes itself into alternating layers, so carbon does not need to travel fast. And that is why the pearlite structure, we could say that it's become striped. Okay, and let's discuss the mechanical property order. So if we were to make a comparison from, let's say, softer to harder, so we have ferrite. Ferrite is softest. Then we have pearlite. Pearlite is in the medium, and cementite is harder. So the perlite is usually called the mix of both, and it's like has a balanced properties, okay? And for steels, the softest would be hypoeutectoid, then the medium would be eutectoid, and the hypereutectoid would be the hardest one. But one thing to consider is that the ductility is opposite. So in ductility, the hypoeutectoid is most ductile and hypereutectoid is least ductile, because cementite needs a lot of carbon and it is brittle, right? And being brittle is opposite of being ductile. Okay, so then, and let's discuss a bit more on eutectic. So as we've mentioned before, eutectic is working with liquid. The starting phase, so it's called eutectic reaction, and starting phase is liquid, and as a reaction we have two solids. Okay, and we can write the reaction as hold on. Yeah, our reaction would be liquid gives us austenite plus cementite. So liquid transforms into austenite and cementite, and the carbon composition is 4.3 it happens at 1147 degrees Celsius. I would suggest you to memorize this, because teacher might ask you to tell him or her the exact temperature and carbon composition at eutectic and eutectoid points. Okay, so at this point, what microstructure forms? It's an interesting question, because the microstructure that forms in eutectic would be called ledeburite. So ledeburite is mix of austenite and cementite, and it is formed from eutectic reaction. And what happens after further cooling? So the austenite inside the austenite you see here, after further cooling, let me write it, after further cooling, it transforms again. After further cooling, it transforms again. So final cooled ledeburite often becomes just perlite and cementite. Okay, so ledeburite itself looks like a more complex network. It's eutectic mixture, and it contains much more cementite. Let's see if we are given the ledeburite structure here. Unfortunately, we are not giving ledeburite structure, but it would be very similar to perlite structure, but we would have much more cementite, so probably it would be something like this. So I will try to illustrate it. Yes. Okay, so I hope it's clear. As you can see, the ledeburite structure difference between perlite, so it would probably have more cementite. It would have like more darker spots as it has more cementite. Okay, so then we have the important flow of cooling. So eutectic alloy cooling. When we are doing eutectic alloy cooling, at high temperature liquid exists. So at eutectic temperature, as I've mentioned, I'm just doing reviews so you guys understand better. So at eutectic temperature itself, so this is called our eutectic temperature, we have liquid gives us austenite and cementite, and later the austenite is replaced with perlite. And one important thing is that at eutectic composition, entire liquid solidifies at one single temperature, and that is also why it melts sharply. Okay, so like pure substances, and that is something that would be industrially important for you, because you can see that one temperature might change everything. Okay, and here just I want to show you, like at higher temperature here we have the layers of, we just have austenite, and then further as the temperature decreases, as I've mentioned before, you right, that the ferrite is in the low temperature, and austenite is in high temperature, right? So we here at higher temperature we have austenite, and as it starts decreasing, the small, like how would I call it, the bundles or something of the austenite, the bundles of the ferrite, they start forming. Okay, and then they turn into alternating structure like this, and as we move further we also have the perlite structure. So I hope the iron carbide diagram is more or less clear for you. Thank you for watching this video. Have a nice day.